Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 193 and 194, and we are discussing assignment number 13. So today we will take up problem 5, and if time permits, we will include problem 6 also. So first of all, we consider problem 5. This is the problem. Let us read this problem. Is it possible to bring a CaCO2 mixture at a total pressure of 1 atmosphere into contact with wait a bit into contact with liquid aluminum at 700 degrees centigrade, which is 973 Kelvin, without having either solid alumina or solid aluminum carbide form. These are the data. This is standard phenomenology of formation of CO2, CO, Al2O3 and Al4C3, aluminum carbide, aluminum oxide. This is the problem. This is the okay, and this reference is Dr. Gaskell, Purdue University. MSc 360 is the course name. Final examination 1987. That time I was working for Professor Gaskell as a PhD student at Purdue University. So that problem actually I came across. So this has been taken. This yes, this is the solution. This side. This is the solution with the help of I'll discuss. And first of all, actually I tell you what. First of all, the strategy is this: how to solve this problem. First of all, we will draw aluminum carbon oxygen stability diagram. This first we will draw. And showing the stability fields of aluminum liquid, alumina solid, and aluminum carbide at 973 Kelvin. So this will first part. Then what we will do, superimpose on the, this is the diagram. This is diagram. This 1, 2, 3 lines. That makes the stability diagram. Then we will superimpose on it a P total at a total pressure of 1 atmosphere, that is PCO plus PCO2, the two participating gases. So PCO plus PCO2, if you consider O2, O2 is always negligible. So PCO plus PCO2, no problem. Okay. So total pressure of PCO plus PCO2 of 1 atmosphere, that line, this is the line of total pressure of 1 atmosphere. But total pressure is PCO plus PCO2. So that line is, this is the line, the dotted line, that will be superimposed on this, and we will arrive at the answer to this question. This we'll discuss actually. This is a strategy. Remember this plot actually, again I will mention during the course of the discussion, but this is ln PCO on the y-axis and ln PCO2 on the x-axis. And so I tell you something here, this is the, if you consider the x-axis scale, this is the 0, ln PCO2 is 0, means PCO2 is 1 atmosphere, and this is PCO2 is 0, means ln PCO2 is minus infinity. This is the span, actually this I showed. So from PCO2 moving from 0 to 1 atmosphere. Likewise on the y-axis, PCO is from 0 to 1 atmosphere. So when ln PCO is 0, when PCO is 1 atmosphere, then ln PCO value is 0, and when PCO is 0, ln PCO is minus infinity. So this is a whole picture, and it is this drawn. The stability diagram is drawn for temperature T is 973 Kelvin. That is fixed for that fixed temperature, for the given temperature of 973 Kelvin. Here, the question, the problem is to be solved. The answer is to be given. Question is whether we can protect aluminum liquid under a total pressure of 1 atmosphere? Or is it possible to have this aluminum? Oh, I made a mistake here, sorry. I don't know how I made the mistake. This is not aluminum solid. So, habitually, I write solid. This time, this is a liquid. This is the better I rewrite here liquid, not solid at all. So this is above the melting point of aluminum, which is 660 degrees centigrade, but this is 700 degrees centigrade. So it is aluminum liquid and given also in the problem in contact liquid aluminum. So is it possible? Question is it possible to keep aluminum liquid intact under a total pressure of 1 atmosphere? Answer will be obviously, let us see. Let us see what will be the answer. This answer is clearly seen here, apparent here, but okay, I will disclose at the end that what is it possible. Is it possible? Answer probably will be no. Okay, answer will be no. Actually, I am giving the answer, but what it will be, then that is a matter of discussion. Thank you. With this introduction, I will now move on to what is this called problem solution. Solution. What I said, I'll write actually most of the things that what I have already said. That is, first take up. This is a strategy. First take up the construction of the aluminum carbon oxygen stability diagram. Stability diagram at T is 973 Kelvin with LnPCO and LnPCO2 as coordinates. Okay. Then after we have done this, then superimpose on it what will in the P total, which is nothing but PCO plus PCO2. Okay, it is better I give a fencing to this figure, so that you are not at all fenced off. This is fenced off, so you don't have any on it. Superimpose on it the P total is PCO is PCO2 is what total pressure 1 atmosphere. Total pressure of 1 atmosphere in the question is 1 atmosphere line. On it the P total is 1 atmosphere line. I mean this line is this dotted line. Superimpose this on this stability diagram line to arrive at the answer. This is the plan of work. Next, take up one by one construction. construction. First we will draw, this is basically 3 lines. One is alumina, follow this. This line is, okay, along this line alumina and alumina oxide, which is alumina. This is aluminum and alumina, Al2O3. This coexistence of these two phases and the gas phase along this line, I have given a name to this, I have not. I have not given a name to this. This line will first draw this, okay. This is O, this is a triple point is O, okay. You will give a name to this, OA, in case you are interested, OB, and this is OC. These 3 lines will draw in sequence. First of all, consider alumina and alumina, aluminum and alumina. Al, so construction first, aluminum liquid and alumina solid. This one. What is the reaction under study then? 2Al liquid plus O2. This is very easy to write. Al2O3 solid. I'm sorry. This should be written in terms of CO and CO2. Okay. CO, right? CO gas plus, okay, CO2 gas rather, CO2 gas plus CO gas. This is Al2O3, this will be 2Al. Now 3O, it must be 3CO and this will be 3CO2. This is the balanced reaction, call it equation 1. So let us see. So now I tell you one thing today. See, to draw this line, namely OA, suppose you are interested in the slope of the line, which is most important. And another thing is also the intercept, where whether it is, suppose you know the slope, then it can be any parallel lines to the slope. The slope will be 1, I am coming to. The slope is 1, I have shown. And I explain, say this 1, so it can be many lines, so that is governed by which one will be by the enthalpy chain. Okay, so these are to be precise, this enthalpy change is also required, but slope, the entropy, negative, that is there. But I tell you one thing today, easy way, quickest way to know the slope is see this reaction and see which is the y-axis. ln PCO means PCO you consider. So CO you consider. For 1 of CO y-axis, so follow that rule. Y is mx plus c. What is the slope? This is the slope. For 1 y, how many x? That is the slope. 1 y here, ln PCO or PCO or simply CO. For 1 CO, how many CO2? For 3 CO versus how many CO2? 3 CO2. For 1 CO versus, so corresponds to 3 CO corresponds to 3 CO2. 1 CO corresponds to 1 CO2. 1 CO y. So this is the slope. And you see slope is what? 1. I have written also 1 slope. This is slope 1. Next will be slope half, and the last one will be 3/4. Easy, quickly. For 1 CO, since it is y-axis CO, 1 CO, how many CO2? Just ask me. 3 CO is pitted against 3 CO2. 1 CO, 1 CO2. I tell you here, since I am talking, it may happen sometime you have come across also previously in copper sulfur oxygen system or other. If CO and CO2 for some reason for some, okay, for the in the balanced reaction appear on the same side. Here you see it is on the right hand side and left hand side. Then slope will be positive. Positive. If they are on the same side, say 3CO plus 3CO2, then 1 CO against is actually against 1 CO corresponds to 1 CO2. Slope is 1. But since on the same side this is negative, this is just in passing I ask you to note this. Okay, if they are on the same side, why negative slope sometimes we get? Today we will not get, everything is positive. Everything is positive. But this previously you got this. So quickest way to get the slope, see look at the y-axis and see the x-axis. Again, another way I'm telling you, see how why it is so. So this is actually the rough work. So see, I'm showing you. Say K, consider K. K what temperature? 973. K 97. Equilibrium also. You don't have to be precise. Equilibrium constant is what? KT. KT is what? Right? You know, PCO cubed, PCO2 cubed. You will get the answer now. Take a ln of this, or 3 ln PCO is 3 ln PCO2 plus ln K, KT, ln KT. Okay. So 1 is ln PCO against it is straight line, linear relation, linear. So what is this? So ln PCO or ln PCO is what? ln PCO is what? ln PCO2 plus 1/3 ln KT. Clear? So this is your y. Y is mx plus c. Y. This is your x ln PCO2. What is m1? 1, that is your m. The slope. Slope is 1. So this is also another way. Okay, you don't have to consider this. Okay, you, for your own satisfaction you will do this. But quickest 1 CO against how many? See the y-axis. 1 unit of y-axis. So what is that? ln PCO means CO. 1 mole of CO. Like this. Y is the y-axis. 1 of this corresponds to how many of x? If it is m of x, means slope is n. So similarly, the slope is 1. So so I will not take up this. Let us move on this. So I am writing this answer. So first of all, get the delta G0. First of all, very important for us to delta G01 is what? Alumina solid standard financial formation for this minus 1687000 plus 326.8. This you know. This is alumina plus 3 CO. What is CO? Delta G0. CO is what? Minus 11700 minus 87.65 T. Then what? This is the product side. Then minus reactant. Reactant is the compounds should be considered only. So aluminum, no question. CO2 minus 3 CO2. 3 times CO2 is what? CO2, yeah, right, stop. Minus 394100 minus 0.84 T. So this is your result, delta 01. What you will get if you do this simplification? Then you get minus 839,800 plus 66.3 T joule, 370, okay, 370 joule. This is the delta G01. Okay, I'm coming to this, and before this, I note here. Here you note, since 1 mole, that what I said here, the slope. Just mention that slope 1 slope, okay, slope 1 of L liquid, L2O3 solid line. What is this line named? I am named here now OA, line OA, so line on what plot? LNPCO versus LNPCO2 plot, and which is nothing but which is referring to figure 5. You all said. So this is mentioned 1. Okay, and the reason is 1 mole CO corresponds to how many moles of CO2, that is the slope. Okay, so this is so can I remove this unnecessary? I remove this unnecessary. Okay, so this is this one, but this is not the end of this. Or you continue delta G0 or delta G01. What is the temperature now? Put the temperature. It is 973. Is nothing. If you do this substitute here, T 973 for T, so you get this value, minus 775 triple 2 joule is okay, is nothing but minus RT ln K 973. What is, write this out, is minus 8.314. What is the T? 973 ln, what is the equilibrium constant? Write nicely. Activity of alumina solid, you know, this will disappear because this is activity of 1 PCO cubed, PCO cubed by activity aluminum liquid squared PCO2 cubed. Oh, cubed. Okay, this is 1 because pure, etc. So if you do this, or what you are getting, just ln PCO some rearrangement, okay, some simplification, take ln on this. So ln PCO minus ln PCO2 is 31.94. Call this equation 2 and give a box. It is so important. From this also, suppose you have found this, then also you have got not only the slope but also its exact location, because slope is known 1 does not mean that it must be this. It can be any other parallel lines which have the same slope of 1. So like this parallel line, slope 1, 1, 1, 1. Which one? Now that is governed by this quantitative values from this, actually given by this delta H0. So these calculations actually which has taken care of all this delta H0, delta everything, delta H0, delta S0. So through the equilibrium constant delta G, which is related to delta G0, these are all taken care of. So which one, since you have quantitatively found the relation, not just okay from the stoichiometry, 1 mole, 1 mole CO corresponds to 1 mole CO2, so slope is 1, but is totally explicitly known. So you can, so from this also you get the answer. Not only the slope, for the exactly which line it will be, where it should be located, because these values is clear. So I am showing you here alongside the rough work. See ln PCO, which is y axis. Ln PCO is ln PCO2 plus 31.94. Is it? So call it y, call it x. So 1 times ln PCO2, okay, is x, and 1 time x, m is 1, okay, it is x means how many x? 1. I'm writing here 1 ln PCO2. So 1 x, I'm sorry, 1 in bracket x, y is mx plus c is 31.94, y is mx plus c. So m is what? Slope. So slope, you get the same result from this also. And not only that, see interceptment, where it should actually, should be located, exact precise location of this line AD, you know from this, okay. So this part is over, I am removing this. So one line is over. Again, you remember, you very well remember, along, this is along the line, these two phases, aluminum liquid and alumina, Al2O3 solid, they coexist along this line AD. So above the line and below the line, as I have told you, see this, if you increase the CO2, then alumina will be stable. CO2 increases this way. So from this, if you move this way, alumina is stable. And if you decrease the CO2, this way, sorry, this way, other way, then aluminum liquid will be stable. Considering CO also, you will get the same result. So if you increase CO, say here, increase CO, from this CO increases, push this way, aluminum liquid is stable. See, you see this, see. So above it, aluminum liquid, and obviously opposite will be below it, the other one, alumina solid. When PCO decreases, so PCO decreases, so actually alumina will be, these reaction will shift towards the right, alumina. So above aluminum liquid, below alumina solid, and along the line AD, aluminum liquid and alumina solid coexist. Finish. First one is over. I'll take up next one, what? Aluminum liquid and aluminum carbide. And then what? Aluminum carbide and aluminum oxide, Al2O3. So this is okay, one by one. So one over, second one, Al liquid, Al4, C3 solid. Again, first of all, you have to write the balanced reaction, okay. So this is important. Aluminum liquid you write like previously, then you write CO gas, then write aluminum carbide solid, then you write CO2 gas, call it equation 2, or 2, I am sorry, 2 is already used up, 3, 1, 2, 3, okay. So first of Al4, so it will be 4Al, no problem. So you do one thing here, okay, 3, 6, if you make it 3, 3, 3, Al4, C3, CO, and CO2. I think I have written correctly. Okay, yeah, this actual, sorry, this should be 6. You please check this. I think now it is correct. 4 aluminum is okay balanced. 6 carbon, 3 carbon plus 3 carbon, 6 carbon, right hand side also. 6O and 6O. Makes sense. So this similarly proceed. What is the slope? That is very interesting. This is your okay okay your job to give me the answer now. This time I have taught you how to do this. So slope will be what? You should write first of all, write this out here. Slope right here. What is the slope? Slope, what I told you, for 1 mole of CO, how many mole of CO2? CO on the y-axis, for how 1 mole of CO. 6 corresponds to 3. 1 corresponds to 3 by 6, half. Half is the slope. See there, half is the slope. This is the line where aluminum liquid and aluminum carbide equilibrium occurs and they coexist. Okay, slope. So this is the slope. Okay, I'm not going to the entire discussion. Slope. Okay, half. Yeah, I'll show you also. Similarly, from similar equation also I'll show you. Okay, but let me write here slope half. This is the quickest way to draw the slope without any calculator or anything. You can draw this diagram, stability diagram. You remember in copper sulfur oxygen, I actually used the slopes and drew the entire diagram. Slope up, slope half. What's the slope? Half of which line? Aluminum, liquid, and aluminum carbide, solid line. Which is that line? It has given name. I have already given name OB. Line OB. Here that line OB. You know, line OB. Line line on log like this on log PCO versus log PCO versus log or ln, since it is ln, right correctly, ln PCO versus ln PCO2 plot, and that is nothing but figure 5. This comment you made, okay, slope is clear, plot figure 5, okay, very good. So but you will get the slope explicitly also, so this is a quick way. How? Now this same way, like this. So how will you get this? Get the delta G0. Get the delta G0. Apply this minus RT ln k. So delta G0 2, it is 3. What? First of all, take aluminum carbide of delta G0 aluminum carbide where? Get this here minus 26500 plus 95.1 T. This is aluminum carbide. Then who comes? 3 CO2, 3 times delta G0 of CO2 is where? Right up there, minus 394,100 minus 0.84 T. This is the right hand side, product side, reactant side, aluminum ignored, aluminum, okay, only compound should be considered from the definition, plus 6 times. So it is actually plus means reactant, so minus 6 times delta G0 CO minus 11170 minus 87.65 T joule. Okay, very good, no problem. So what it results actually, clearly see, check this, is exactly. Okay, so what you get, answer is minus, write nicely, minus 777 100 plus 618 0.48 T joule is okay. Joule. So delta G02 is function of temperature. So like this, delta G09, okay, delta G02 or 3 rather, 3 for temperature 973 is what? Put the value T here, value of T 973 here, you get the what value? Minus 175,319, minus 175,319 joule is equals to what? Minus R T ln K3 973 is what? Minus 8.314 as you write. T is 973 ln K3 expression from this is what? What is the equilibrium constant expression? Is what? Activity of alumina carbide, and that is solid, pure solid, times PCO2 cubed over activity of alumina liquid, which is also pure, power 4 times PCO power 6. Power 6, okay, that's it, of which this is 1, this is 1, 2. So what you are getting from this, if you just little bit simplify, it will be, well, it's very good. It will be nothing but is okay, very good, very good. So you get, see here, ln PCO2 3 and it is ln PCO 6 times 6 ln 3. If you take this 3 common actually, then you will get this. Obviously, you can guess this ln PCO2 3 ln PCO2. If you divide by 3 ln PCO2, and it will be 6 ln PCO divide by the same 3, 2 ln PCO. So and then this is actually opposite sign. So let me write this ln PCO2 minus 2 ln PCO is what? 7.22. Call it equation 4 and give a box. Highlight this. This is equation 4. Good. Now we actually find out. So they intersect where? AO, BO intersect at O. That will be actually the triple point. Then from this O will emerge OC, the next equilibrium between aluminum carbide Al4C3 and Al2O3. That is the third line that I will draw. So this will be a triple point. So we can, if we solve these two equations, we get the value of PCO and PCO2. So triple point value as PCO I have written here 9.48 times 10 to the power minus 18 atmosphere PCO, and PCO2 is what? 1.32 times 10 to the power minus 31 atmosphere. This I am showing here. Okay, just solve these two and 4. So for this, I don't think you need this. Solution is continuing. Just remove this couple of lines. Just 2 and 4. You work with this, adding 2 and just you add, then you see automatically PCO2 minus PCO2 plus PCO2. Just add. Adding 2 and 4. Oh, give a star. Give a star here. Star here. Adding 2 and 4. what you get? Minus ln PCO, add this minus ln PCO is what? 39.16, or PCO is what? Is 9.48. PCO is 9.48 times 10 to the power minus 18 atmosphere. Okay, write nicely atmosphere and make the fencing like this. 1 out PCO. If you know PCO, substitute here, get PCO2. And from 2, now from 2, so this is very important result, underline. From 2, what is this? From 2 here. Hence, ln PCO is how much? Minus, see, ln PCO is minus 39.16. Substitute here. Minus, or shall I write here? ln PCO2 is what? Right? ln PCO2 is what? Nothing but ln PCO minus 39.14. 31 point, I'm sorry, 31.94, I'm sorry, from here, from 2. What is ln PCO? Is minus 39.16 minus 31.94, 31.96 is minus 71.1, minus 71.1, or it is ln PCO2, or PCO2 is what? Or PCO2 is, write nicely, PCO2 is what? 1.32 times 10 to the power minus 31 atmosphere, again underline. So these two pressures, this is actually describes the triple point O. So I have given here, see, PCO is 9.48 times 10 to the power minus 18, 9.48 times 10 to the power minus 18, and PCO2 is what? 1.32 times 10 to the power minus 31, 1.32 times 10 to the power minus 31, and so it is already done. So two curves already drawn, and triple point, okay, coordinates are also known actually in terms of PCO and PCO2, or ln PCO and ln PCO2, no problem, no, fully know. We have not yet drawn the curve OC and OC representing the equilibrium of aluminum carbide and aluminum oxide. This will take up. Next, shall I remove this line? No problem, this is already used up. We will not come back to this one, okay? We don't require this anymore. So next is what? Gradually is Al2O3 solid and alumina carbide. Solid, both solid. Okay, what is the reaction? 2Al2O3 solid plus 12CO gas goes to Al4C3 plus 9CO, solid plus 9CO2 gas. Call it equation, obviously in the line is what? 1, 2, 3, 4 is over, so this must be 5. Equation 5. Yes, correct. So you please check the balance, okay, quickly. 9 carbon and 3 carbon, 12 carbon, right hand side, and left hand side Al4, oxygen 6 and 12 oxygen, means O, I mean 6O and 12O, 18O and 18O. So it is actually correctly balanced and no problem, we move on. Hence, tell me again, very interesting, I remove this line, don't require anymore, all over, just here. So tell me, so what is the, suppose you don't actually, I am not going for actual detailed finding out the equation, but slope will be good enough. You can do the same way, you can delta G0, etc. But for the time being, you just tell me the slope. Answer me. See, for 1 mole of CO, how many moles of CO2 is corresponded? 1 mole of CO corresponds to how many mole of CO2? That is the slope. 12 mole CO against 9 mole CO2. So 1 mole CO, 9 by 12 means 3/4. 3/4 will be the slope for this curve. See, 3/4 slope. So let's write that out. Okay, very easy. So now, hence the slope of Al2O3 solid and aluminum carbide solid line, and the name of this line, right? Nothing, line OC, and OC on ln PCO versus ln PCO2 plot, which is figure 5, is what? Is nothing but I am writing for 12 CO corresponds to 9 CO. Yeah, yes, see at the bottom. Star is okay. Okay. Is thank you. Okay, 12 CO corresponds to 9 CO to 1 CO, 9 by 12 is 9 by 12, that is 3 by 4, 3/4 slope. So is 3 by 4. That's it. So this is one, very easy for you to draw. This is one, this is pretty less, half, but positive, flatter. This is one, steeper, one, this is half, and this is between these two, 1.5 comes to 3/4. So it will have an intermediate slope. Okay, the slope between 1 and half, that is 3/4. So it runs actually this way. So, and if you extend this, it will come between this. If you extend backward, then obviously you can see this diagram is correctly drawn. See, backward, see, it is correctly coming between, so coming this way, means between 1.5 slope. This is a slope 3/4 is over. So this part is over. So first part was construction of the, remember the planning was construction of the diagram first, which is, just let me write one line about the construction. Remove this is all over. Over. So just write finishing lines. Now complete now complete the aluminum carbon oxygen stability diagram showing the stability fields of fields of aluminum liquid, aluminum solid, and aluminum carbide. Alumina, this is aluminum oxide solid and aluminum carbide solid. With the help of LNPCO versus LNCO2 plot at T which is fixed at 973 Kelvin. Figure 5. So this is the end of this. Not the end. Question has not been answered. Only the diagram has been drawn. But you have to answer, is it possible to bring a CO2 mixture at a total pressure of 1 atmosphere into contact with liquid aluminum at 700 degrees centigrade? This is the question. So what we will do next? The next job is superimpose the P total is 1 atmosphere, where P total is PCO plus PCO2 is 1 atmosphere line. This line will superimpose, and then we will decide what will happen to liquid aluminum when it is exposed to a total pressure of 1 atmosphere comprised of CO gas and CO2 gas. This is the question. This is next. So you follow this diagram first of all. Then I will give you the answer. Okay. So just wait a bit. You see with me. See with me. Have you noticed that LNPCO? PCO is 1 atmosphere, one end. PCO plus PCO2 is the P total is PCO plus PCO2 is 1 atmosphere line. You have to draw this. So what are the possibilities? Extreme possibilities what? PCO alone is 1 atmosphere and PCO2 is 0. PCO is 1 atmosphere, PCO2 is 0 atmosphere. Alternative extreme, PCO is 0 atmosphere and PCO2 is 1 atmosphere. These two extremes are where? This point and this point. See, this is PCO is 1 atmosphere, LNPCO is 0. Since it is LNPCO is 0, but means PCO is 1 atmosphere. And likewise, it is LNPCO2 is 0, means PCO2 is 1 atmosphere. These are two extremes when there is no uniquely contributed, alone contributed, sole contributor, CO here sole, CO2 here sole. When this is actually mixture, so actually, so this is actually so this is so so this then if you draw this diagram, so this will be this 0, this will be almost horizontal, and this is almost vertical, almost slightly shifting, and this is also slightly descending, and drooping, slightly negligible. Because why? The scale you follow the scale. Have you noticed this? This one broken lines. So what is the span here? Since we have to accommodate both zeros, not only ones, zeros also as the extreme. PCO is 1 atmosphere when PCO2 is 0, but when PCO2 is 1 atmosphere, then PCO is 0. So 0 is to be shown also. So when PCO is 0, this point origin as it, so LNPCO is minus infinity. So if you want to show minus infinity, this is simply 0 to minus infinity in terms of ln PCO. So what it will be? So 0, suppose I give you minus say ln 0.5, say for example. The PCO is 0.5 atmosphere. So what is the value? You know, ln 0.5 is standard 0.693 minus 0.693. Okay, ln 2 is okay, ln 0.5 is minus 0.693. So this will be, this is 0 to, so this will be, when it is 0.5, it will be minus 0.693. So where it will be located? If it is minus infinity, 0.693 means minus 0.7. Say minus 0.7 will be, you cannot see it is actually extended to infinity. So minus 0.7 will be very close actually. So this is a 0.5, say like this. So this is the understanding. So you draw this almost horizontal, and you also draw almost vertical, and then here where they are about to intersect, there this will be actually where you have these distributions. What are the distributions? Say like say 0.5, 0.5, 0.3, 0.7, 0.7, 0.3, 0.8 systematically. So 0.9, 0.1. It is 0.9 issue to 0.1, 0.8, 0.2, 0.7, 0.3, 0.6, 0.4, then 0.5, 0.5, which is actually minus 0.693, minus 0.693. How will so? This is minus infinity, this length. So this will be actually almost superimposed. That's why there is almost no change. Here there is a small change here. I have shown here. Okay, this is there. This may be actually minus 0.693. This may be. Similarly, CO2 or what? Okay, 0.5, 0.5. Then what? Keep on further decreasing CO 0.4. Then CO2 is gaining 0.6, 0.3, 0.7, 0.2, 0.8, 0.1, 0.9. Again 0, 1. That is this point. This point. So that's why this is, if you draw this, you will have this. That is actually is almost vertical, almost horizontal, and there is a bend there, small bend there. Okay. So why I am talking this? You first absorb this, that one atmosphere total comprised of PCO plus PCO2. That line must be drawn correctly. Otherwise, how will your answer be correct? So, if you consider this answer, this is drawn correctly, then I say consider it is actually somewhere here. Okay. So this is, or say where suppose here, okay, where CO is predominant. Here CO is predominant. Here completely CO, pure CO. Then CO is predominant, and here is CO2 predominant. CO is pure and CO2 is predominant, and here almost there is a share. Okay, say 50-50 share or 60-40, 30, 40-60, etc. So here, suppose here gas composition is this. Say it is say 90% CO, 10% CO2. Say this point. What will form? Is aluminium will remain intact. Here, who is stable phase? What is the stable phase? That's why we drew the diagram, stability diagram. Aluminum carbide. If the gas composition, what you say, aluminum carbide, okay. And suppose it is actually predominantly CO2, say very close to 90%, say 90% CO2, 80% CO2, so somewhere here, say here, who is the stable phase? Aluminum oxide. So in this case, aluminum carbide will form. In the other case, aluminum oxide will form. I am repeating. In this domain, follow me. In this domain, who is stable? Aluminum carbide. Not aluminum liquid. Aluminum liquid is way down here. It is secured here, secluded. In this small window, it is there. 1 atmosphere way above. See, imagine what are the pressures here. 9.48 times 10 to the power minus 18, this point, and 10 to the power minus 31, minus 18 minus 31, 10 to the power. 10 to the power minus 18, 10 to the power minus 31. See how small pressure here. And there aluminum is sitting there secured, safe, protected, unhurt, unchanged. But our actual line, total pressure one line will run like this. If it is in this domain, if it is in this domain, who will be stable phase? Aluminum carbide. And if it is in this domain, who will be stable phase? Aluminum oxide. This is the answer. You may argue, sir, if it is suppose say here on this point, then both aluminum carbide and aluminum oxide together will be stable. But never ever aluminum liquid. Aluminum liquid will convert. So your answer will be what? That aluminum will be converted to aluminum carbide or aluminum oxide L2O3 depending on the relative values of PCO and PCO2. That's it. And this diagram you just present and you get the answer. Okay. So only I repeat, only when it is here hitting here on this curve where aluminum carbide and aluminum oxide coexist, exactly this precise point, then they're both. Who both? Aluminum carbide, aluminum oxide. Both will be present, but never ever aluminum liquid. So your answer. So your answer is what? So couple of lines. Answer final. So under 1 atmosphere total pressure, which is PCO plus PCO2. Remember, PCO plus PCO2, aluminum liquid. No, I give another thing I tell you. What will be the answer? Is it possible to bring a CO2 mixture at a total pressure of 1 atmosphere into contact with liquid aluminum at 700 degrees centigrade without having either solid alumina or solid aluminum carbide? Your answer is no. No, it is not possible. One of them will form. And who will form? That we are writing. And a unique situation where they both will form. But this I am writing. That is actually, but main thing I am writing aluminum. That is, aluminum liquid will never be. It is not possible to bring a mixture into contact with liquid aluminum. Okay, because liquid aluminum will change. So it is not possible to keep liquid aluminium intact. Intact, unchanged. It is not possible. So aluminum liquid, what else will either convert into aluminum carbide or alumina solid depending upon the relative values of PCO and PCO2. That's it. That's it. Okay, given relative value. So this value this. Okay, this once more. This is that means this is the domain where this is the domain. Yeah, aluminum carbide, and this is the domain aluminum oxide, and only this point is on line AC. This one precise point, both of them will be will will be stable and will coexist. Okay, will be together. But aluminum liquid never. This is not possible. See, thank you. So this problem is over. We can give say over. Let us take up. Since we have some time left, so I will take up one problem. Problem 6. So let me remove this. Problem 6. I'll take a very interesting problem. It's a different kind of problem, but very interesting. Okay. I'll keep this fan. Let's have it. So let me remove these things all. So I'll take up now problem 6. Last problem. This is a different kind of problem. Very interesting that I'll take up. A different kind of problem. Here I will actually, I tell you what, this last problem, see this actually struck me when I was solving some problems. I actually, I wondering how many variables like temperature, partial pressure, I must provide as a teacher. I as a teacher must provide to my students so that he will be able to solve the problem. Normally we take from books. Author has Authors have designed the problem. The author has designed the problem. But what is the rationale behind this? What is the science behind this? What is the thinking behind this? Why only these two data are given, like temperature, partial pressure of one species? Why not other species also? Any other species out of say 4, 5 species, or two species given, temperature given, not third species, fourth species. Why? Or why not one species only? This actually struck me, and this actually I was as trying to resolve this. This is actually a phase rule problem. If you have mastered the Gibbs phase rule, then you have no problem. You will understand how it can be, how the problem is to be designed. What sort of data you should give. Data means not thermodynamic delta G zero data. No. It's the problem text problem. At this temperature, pressure, it's mainly this. In case of solution, maybe composition also. But as consider pure condensed phases. And this problem is about that. So I'm just giving you in details. If you follow me, you will enjoy this problem. This is the last problem of assignment number 13. Last additional problem. I write this. I write this as assignment number 13 continue. I write this additional problem. Since we have some time, so we can utilize the time. Additional problem. And additional problem. Problem 6. Problem 6. Okay. Questions. How to design a multi-component multiphase chemical equilibrium a multiphase chemical equilibrium problem using the concept of the Gibbs phase rule. How to design. This is particularly important for teachers. Okay, for students also, but more for the teachers. More important because teachers design problem and hand it to students for solving them. So important for the teachers. Teachers. So what is this? Suppose you follow this. Suppose the question. This is the question. I am answering. Just explaining further. Okay, but this is the main question. How to design. Suppose I'm outlining the system. Then I'll take up the design or the data that you must provide to the students. That is the design. How you will design the problem. Suppose you are actually as if making up a problem, Instead of answering, you are used to answering a problem, solving problem. But today you are as if learning how to construct a problem. Very interesting. The other way around. Okay. Suppose zinc sulfide solid and zinc oxide solid are initially taken with a gas mixture of H2, H2O and H2S hydrogen sulfide and allowed to in a reactor and allowed to equilibrate. Allowed to equilibrate. It is considered that it is considered that what it is considered that the zinc sulfide solid and zinc oxide solid are at equilibrium are at equilibrium with the resulting gas mixture what H2 H2O H2S that was initially fed, then through reactions many other gases produced. What they? For example, sulfur. Sulfur will be there, and then oxygen will be present. Sulfur, oxygen. Then you will have what else? Zinc vapor. Zinc vapor may be present. So resulting gas mixture what? When equilibrium will attain, all these gas species are present along with zinc sulfide and zinc oxide, which are taken in sufficient quantities. You have to consider so that they survive the equilibrium state. The reactions and are actually found in the equilibrium state. Okay. Are present in the equilibrium state. So H2, H2O, H2S. What else? As I write, sulfur, H2 gas. I consider oxygen and zinc is actually gas in the vapor, zinc vapor. So how many? 1, 2, 3, 4, 5, 6. And you started with how many? 1, 2, 3. 1, 2, 3. You started. So I'll sketch the problem. Don't worry. Okay? Vapor. Question is how many? Now the question comes. How many information must be given to the student? Must be given to the student. This is the question. How many information? See, I have not said anything about temperature. See in the problem. So I'm sketching you. Acha. I'm sketching you. Acha. Now not yet complete. To the student to allow them to allow them to find the equilibrium state hello just 55 or 7 o'clock just pop in, huh? We may be finished, we are not sure, okay? Maybe early we finished today, okay? To find the equilibrium state in terms of temp temperature, pressure and composition. And composition of each phase. In composition of delta G0, I am not asking. That is not the information. Information in the text. Some are missing. You see, temperature is missing here. Partial pressures, nothing is. Total pressure, nothing is said. Nothing. So I am sketching the problem. Okay. This is how many information should be given. Okay. I'm giving you the part of the problem. I'm showing you. This initial state. Zinc sulfide solid, zinc oxide solid, and the top initially see H2 H2S H2 H2O H2S gas mixture, gas. This is what you write initial state. Initial state. I've already written here. So sketch it. State, non-equilibrium state. Then it moves to equilibrium state. Same reactor. Equilibrium state. So what it is again? Zinc sulfide solid, zinc oxide still there as if they were initially in sufficient quantities, excess quantity. And what are the gases now? Resulting gas is not only H2, H2O, H2S. They are present, of course. Not only that, something else, let's say sulfur has arrived, oxygen, zinc. This is the zinc vapor. So you don't have to write, since I am writing, this is the gas phase, gas mixture. This is what? This is nothing but final state, equilibrium, state, non-equilibrium state, right? Non-equilibrium state maybe, if it helps you. This is equilibrium state. Now tell me, tell me one thing. This you will do, okay? Use the concept of the Gibbs phase rule. You have to use. You will apply the Gibbs phase rule, the concept of the Gibbs phase rule where? Which state? This state or this state? Just ordinary question. After all discussions are over and we are actually taking up the last problem. Your answer is what should be? Sir, equilibrium state. The Gibbs phase rule applies to the equilibrium state. So what you do to find the equilibrium state in terms of temperature, pressure, and composition by using the information means degrees of freedom. What is the definition of degrees of freedom? By fixing, say suppose it is f, by fixing a number of variables, by fixing a degrees of freedom, by specifying a degrees of freedom, the system can be defined. System can be defined completely in terms of temperature, pressure, and composition of each phase at equilibrium. This is actually equilibrium state. Always equilibrium state. Okay. So this is a problem. This is part of the problem. Problem is repeated here. Figure. Okay. Now solution. So what is answer? I will say I don't say solution. Answer. I am giving to this question. How many information? I am writing solution. I am coming to later on. Answer. Writing here. Answer. How you follow me? How many data you will provide? Like temperature. I am giving temperature, total pressure, partial pressure, etc. You follow me. How? From the Gibbs phase rule. The degrees of freedom is the answer. Find the degrees of freedom here. Equilibrated system. Find the F and the answer. That's the answer. Suppose it is three information I should provide to the student. It is two information. And then what are they? You choose from temperature, pressure, and so many partial pressures are possible. Temperature, total pressure, partial pressure, or only partial pressures, not total pressure. Whatever you do, you actually degree of freedom dictates the number of information you must provide. Then all other will be automatically figured out. The system will be, you will be able to define the system and to allow them to find the equilibrium state. Just F variables, degrees of freedom, F. Answer. Start. C is what? How many? C here, tell me. C is, tell me, I am writing. 4. Follow this. What are these? Zinc, oxygen, sulfur, hydrogen. Why? Number of elements. Easy. Okay. And also another definition of C, number of species minus number of independent reaction equilibrium. These also I will use later for the final part. Okay. For actually concluding part. Okay. This in C. What is the P? Number of phases. How many phases? Take a look. I write 3. Who are there? 2 solids. Who are there? Zinc sulfide, zinc oxide, and 1 gas phase. Gas phase contains how many species? You can write this. Keep on writing. H2, H2O, H2S, sulfur, oxygen, zinc. That's it, and give another bracket. P is 3. What is F? Then F is C minus P plus 2. So it is C is 4 minus 3 plus 2. 6 minus 3 is 3. 3 information. 3 information must be given. What are these 3? So answer 3, not 4. No, not exceed. Then phase elimination will take place. A student will complain that it is not actually in compliance with the problem. and don't make it less than 3, 2, no, underspecify, don't underspecify. Then what will happen? The system will not be able to be defined. The student will not be able to define, or he will not be able to define the system. Incomplete. So 3. What are these? Typically what 3? You know very, very convenient is, most convenient you know by this time, that temperature. Temperature is your freedom, choice. Maybe 800 Kelvin, 900, 1000, whatever your choice. But temperature is very convenient. But you may not under compulsion. I told you once and once for all that choice of freedom is arbitrary, and it is actually a matter of convenience. Okay, it is arbitrary. It is independent. Okay, free. Arbitrarily you can fix anything, any. So we say it is a matter of choice. Freedom, degrees of freedom is a matter of choice. Choice. So not necessary, but temperature is very convenient. Why convenient? I tell you. Remember, when you write the reactions delta G0 as a function of temperature, you want to find out the equilibrium constant. So you use delta G0 is minus R3 ln K. So their temperature, if you know, then you could find the equilibrium constant. Once equilibrium constant, then it actually relates with the partial pressures. So you get an equations and you can solve. Solve means you can solve all values of all partial pressures. All partial pressures from that set of equations, which you know actually once you know the temperature. You know the equilibrium constant at that temperature. So you know a number of times, okay, a million times here. So 3. So I'm writing this. So P is 3. So 3. So 3 information. This is I'm writing. 3 information must be given. Must be given. This is the answer. How many information must be given? 3. And now proceed. Now proceed. Let us show if 3 information and what are they, and by using them, how if I can solve the problem. These are actually coming. Okay. Subsequently. So this, what are the 3? 3. Achha. Considering now I'm considering T as a temperature. T is the temperature. T temperature. T as a convenient degree of freedom. D O F. Convenient degree of freedom. The other three information must be given. The other 2 degree of freedom, other 2 degrees of freedom must be the partial pressure, partial pressure of any two out of 6, out of 6, 1, 2, 3, 4, 5, 6, out of 6 gas species, out of 6 any two gas species, any two gas species, 6 gas species, any two, and temperature 3 total. Temperature, I told you no compulsion, it could be actually three gas species possible, but if temperature, it will be easy to demonstrate, easy to solve. So two gas species, like what? Partial pressure of H2. Where? Not here. No, don't look at this. Look, suppress this. Degree of freedom about the equilibrium state. About the equilibrium state. Two values at equilibrium. Say pH2 at equilibrium, pH2O at equilibrium. So two data plus temperature 3. These three information. Or you might say, sir, why, sir? Suppose total pressure? Yeah, possible. So one temperature and total pressure. Two gun, and the third would be any one of them. Say partial pressure of hydrogen, say, or say partial pressure of oxygen, say, or say partial pressure of zinc, say. So temperature, total pressure, partial pressure of zinc, say. I am considering, so anything I can consider, so I am considering just for demonstration. For example, so, or out of 6 gas species, any two gas species, or it may be what? Oh. Or what it can be, as I as I already told. So, or it may be total pressure. You call it P actually, only P. Total pressure P and partial pressure. Plus how many? Temperature 1, total pressure another, and partial pressure of only one. Any one of these 6, and partial pressure of any one gas species, and partial pressure of any one, but one only, or alternatively, or any one gas species. Any one gas species. Okay. Then it will be 3. I repeat again, 3: temperature, total pressure, and any partial pressure of any one. Say for example, since I have written, say partial pressure of say H2S, or say partial, okay, one, any one, okay. Or you may be temperature and two partial pressures, like say any two pH2, pH2S, possible, any two. So, but suppose, now what I am doing, so there are so many options, but I have to do something, okay. So do something. Suppose we choose three as T, and here pH2, these three. Temperature, not total pressure, but two gas species, pH2. Okay, very good. Double star. Okay. Now this we choose. Now we refer to where actually when it struck me. Actually, it was a gas scale problem. Some data given. I'll give you everything. Then it struck me, why not more data or less data, fewer data? Why exactly this data? and why it works. So then I thought of this problem. So I'm giving you that, referring to, maybe here, referring to problem 10.15, problem 10.15, page 318, page 318 of D.R. Gaskell's book, of D.R. Gaskell's book, second edition. Gaskell book, let me write the right name. Introduction to metallurgical thermodynamics, second edition. Second edition. Referring to this, we see that what we see there. Now we see what we see. We have understood what we see. We follow this. What we have chosen? These three he has chosen. What we see that Gaskell has chosen what? We see that the chosen values are temperature is what? 2000 Kelvin. pH2O is 0.5 atmosphere. And pH2 is pH2 is 0.0421. You will find them in exactly these three, not more or not less. It is not very, one of them is given. No, then problem will not be solved. Problem will not be solved, cannot be solved. If it is 3 more than 2, means these two partial processes, and still how many? 143. Okay, it's okay. Come team time, or that's right, very good. If it is less than that, then that is not there. No, it is not. It is not temperature and one of them. No, then you cannot solve the problem. You will under-specify. You cannot define the systematic equilibrium. This equilibrium cannot be defined. So it is not 4, 1, 2, 3, not another gas species. No, exactly 3. Why 3? These 3. 3, 3. This is the design. So let us. I will show you. I will give you the solution then. Now I will show. Now let us solve the problem. Okay, actual. The fundamental things are clear. Now you can solve the problem yourself. But for the sake of completeness, I am solving the problem. And I am giving you the answer also. Not the calculation, you will do the calculation yourself, but I will give the outline of the calculation. So follow me. So, shall I give a star mark here? And I remove this. Remove these lines. It's already discussed. Next part is what? Nothing but got the answer. Okay, so start. Next question. Answer is 3 is okay. We chose and gas scale also, or say the actual values gas scale gave 2000 Kelvin, 0.5 atmosphere pH2O, and pH2 is 0.0421 atmosphere. So next question, what is the next question? Now solve it. So how we can, by specifying 3 variables, how you define the system at equilibrium in terms of temperature, pressure, and composition of each phase. Let us see. So next question, how will a student, question was given to a student, so how will the student solve the problem, given that what gas scale has given. Okay, these 3 once more, right? given that T is 2000 Kelvin, pH2 is 0.5 atmosphere, I'm sorry, pH2O, 0.5 atmosphere, and pH2 is 0.0421. This is damn easy for you. Okay, this is because you have solved how many problems? 5 problems plus, say 6 problems. Say 5 problems, 5 problems already, and 6 already example. This is assignment. 11 problems you have solved, and also you are discussing Gibbs phase rule for so many days, so you can easily. But still, I am showing you how to solve solution. And so I am writing here solution. Here I wrote here answer. I am writing here solution to this question. Solution. Quickly. Acha. One interesting thing is this: I am trying to find out number of independent reaction equilibrium we have at our disposal. Number of independent reaction equilibrium that is required. So that's why I am actually taking up the solution. First, to find out 4. C is how many? 4. You remember C is 4. So 4 is C is what the definition? Alternative definition. It is number of elements. Okay, in terms of this is number of elements. What is the other? Is tell me number of species. Recall minus number of independent reaction equilibria. Number of species how many? Tell me, see the species. How many gas? 1, 2, 3, 4, 5, 6 gas species, and 7, 8. This 7 species, 8 minus number of independent reaction equilibrium. So this is, I am writing here. Number of species is 8. It is better right here. 8 or number of independent reaction equilibria. How many? 8 minus 4 is 4. So 4 reaction equilibria is there. Not more than that. 4. But which are there? Then don't ask. Any 4. There should be mutually independent. Only this. Remember all discussion, those discussions. So solve this problem. I think you don't have any trouble. I am giving the outline quickly. So four reactions, they are helpful. That will help you generate the relationship between these partial pressures, and you will be able to solve them because you are getting equations and solve. So of this, how many you actually got this? Okay, see. Okay, let us start quickly. So four is okay, I guess. Four is okay. Four is okay. Now start one by one. Four independent. I'm writing. See how I'm solving the problem. Follow me. You can do yourself also, but still follow me. H2. I am considering first this equilibrium. H2 gas plus quickly half O2 gas goes to H2O. Vapor means gas. I'm writing. H2 gas. So you know K2000. You know very well from the delta G0 is what? Write nicely. pH2O over pH2 PO2 power half. You know, this is actually, you may write, you may not write, but if you understand, very good. The out of this, which value you know, what are the given? See gas scale problem. So here also, here, okay. What is the, say here? Say what is the pH2 is how much? 0.5. Article here. Refer to this figure only, not this. The initials. This Gibbs phase rule applies here. So 0.5 here it is pH2 is 0.5. pH2 is how much? 0.0421 and K2000 K is delta G0. Data can be obtained from data book. Delta G0 is known, so is minus RT ln K. So K2000 is known, so it is known quantity. So this gives you obviously all known. So PO2 is known. One of them out. Remember all 1, 2, 3, 4, 5, 6 of these two. How many you know? 2 you know, 4 you have to find. Oh, that's why you have 4 equations. That's why I say 4 unknown remaining here. Out of this 6, 2 are given, 2 partial pressures are given. So 4 partial pressures are to be found. So 4 equations are necessary. Hence 4 reactions. That's why 4 independent reaction equilibria you have. Very consistent, very consistent. So first, second, tell me oxygen being known. You take up. I'm doing it here. I'm removing this. Oxygen is being known. What you may consider zinc plus oxygen goes to zinc oxide. Zinc vapor. Follow me. Zinc vapor. Okay. Plus half O2 gas is zinc oxide solid. What you have? Then it is better I write here. K2000 again K2000, which is known quantity, is what you write? Activity of zinc oxide solid over Pzn PO2 power half. This is a known quantity. This is a pure solid one. PO2 a moment ago you have found. So this is known. So this leads to what? Pzn is known. So you encircle this better. Encircle. 2 out, 2 down. Okay, zinc here down. Okay, next take up third. So zinc is known. So you actually hook up with the zinc sulfide and sulfur. So that you do. Zinc vapor plus half H2 gas is zinc sulfide solid. Happy? Okay, this is K2000 again here. Remove this lines. Okay, interfering, no problem. Okay, K2000. Tell me. Or write the expression activity of zinc sulfide solid Pzn Ph2 power half of which this you know, and this is 1. Pzn is known here moment ago. Pzn is known. So this leads to what? Ph2 is known, found. What remains? What remains? You see, what remains now? H2S is not yet known. All other nodes. Okay, 1, 2, 3 are found. 1, 2, 3, and 2 are given. 5 out of 6. 5. 6 is what? H2S yet not known. For this, what you consider? Which equilibrium consider for H2S? H2 plus half H2 goes to H2S. Simple formation reactions. Okay, no problem. Very easy. Simple, short. Okay, so H2 gas plus half H2 gas is H2S gas. So K2000 is what? You may write here, okay? Right here, right here, right here. K2000 is what? Right, nicely. PH2S, PH2, PH2 power half. Okay, at equilibrium I can write. Yeah, I have not written, but these are all equilibrium. Okay, at equilibrium. Okay, known. PH2 is known, given 10421, known. Yeah, for equilibrium state it is given. Okay, so PH2 is given. Okay, fine. PH2 a moment ago, PH2 power half is known, reached to PH2S is known. So all species, all partial pressures are known, means composition is known. So what is the total pressure? If you ask me, last question maybe you may ask me, what is the total pressure then? Total pressure must be temperature, pressure and composition of each phase. Composition of each phase, okay, these are pure solids, so you know composition is mole fraction 1, pure. And composition of gases, you know partial pressure means you know the composition means mole fraction by partial pressures of each values by total pressure. What is the total pressure? That is also required. Total pressure you want to know. P is the total pressure. P is P total. What are they? Add plus 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 P hydrogen. You write this plus PH2O plus PH2S plus PH2 plus PO2 plus P zinc plus all you know, all you know. No, you know this, you know this, you know this. Sorry, you know this, you know this, you know this. So total pressure is also known. Total pressure you know. Okay, so this is P all you know, total pressure. Hence you know the temperature. Total pressure means pressure of the system, temperature of the system, and composition of each phase. Each phase when these two solids are pure, so their mole fraction is 1, and gas phase how the composition is, mole fraction is nothing but partial pressure, which you know for each of them you know, by total pressure, which you also know now. So you may write that line. Okay, hence remove this, hence you may write concluding line, hence temperature, pressure and composition of this, hence temperature, which is T, pressure P, and composition of each phase at equilibrium is found out. So just by fixing 3 variables, by fixing using 3 degrees of freedom, giving 3 information to the students, a student can find out. Okay, here I can write for composition for pure solids, pure, huh? এই যে আমরা for pure solids composition mole fraction is what 1 for zinc oxide and zinc sulfide, and for gases xi, say the I is the chosen species, is what, tell me, pi by total pressure, which both you know, partial pressure you know and total pressure you know, which is summation of the partial pressure. So each case mole fractions you know means composition you know. So this, so here you can say thank you very much. Okay, with this we have solved the problem 6. This is a new type of problem. Thank you very much. Thank you very much for your attention and for your interest and for your patience, for your devotion and for your sincerity. Thank you very much. So we have assignment 13 over, completed, right? Assignment number 13 completed. We will take up a new topic. We will take up new topic at the next class. Okay, that I will announce in the class itself. Okay, so today we are actually done today, and we have completed this class, and we are. Thank you very much for your everything. Okay, and okay, see you in the next class. Okay, see you. Bye.